Thank you so much, Dr. Dandapani. It's a great honor to be part of this webinar series and to chair this session. Let me briefly introduce our speaker today, Dr. Jae-kwang Kim, known as Jae to many of us. Jae is the liberal arts science dean's professor in the Department of Statistics at Iowa State University. He grew up and received his university education in Korea. But then he moved to the United States, pursued his doctoral studies in statistics at Iowa State University under the supervision of Professor Wayne Fuller. After graduation, he worked at a few places before eventually coming back to Iowa State in 2008. So his early research work focused on missing data problems and imputation techniques in survey sampling. And his 2004 Biometric paper with Wayne Fuller on fractional imputation is widely cited. He is a leading researcher in the field of survey sampling, and his work covers many theoretical and applied aspects of survey sampling, as well as general statistics. Among many awards and honors he received, he's a fellow of American Statistical Association and a fellow of International Institute of Mathematical Statistics. So his talk today is titled Multiple Bias Calibration for Valid Statistical Inference with Selection Bias. Jae, it's all yours.
Thank you, Changba, for the nice, very nice introduction. And hello, everyone. Good morning, those in the US and Canada, and good afternoon to those in India. I'm very honored and very pleased to give a presentation today. And let me first share the screen. Okay. Oops. Okay, can you see it?
Not yet.
Not yet. Okay, sorry. Okay. How come? Okay, how can I?
Yeah. Okay, yeah. No, we are good.
Okay. Thank you. Thank you. So yeah. So let me start my presentation today. So the title is Multiple Bias Calibration for Valid Statistical Inference with Selection Bias. So it is about how to correct selection bias in voluntary sample. And this is joint work with my Sang-Won Cho, who is my postdoc, and Jong-Len Wang is my former PhD student. He's now working in China. So I'm going to start with a very general setup where X and Y is follows from a distribution, unknown distribution F. And I'm going to use red color to denote unknown. So parameter, unknown parameter will be expressed in red color throughout this presentation. And now instead of observing Xi, Yi for all unit in the population, we observe Xi, Yi only when delta equal to 1. So delta is basically the sampling indicator. So delta equal to 1 if we observe Xi, Yi, and 0 otherwise. And assume that delta is a binary random variable with IID distribution. So delta I is IID with binary pi Xi and Yi. And so this function is called propensity score function. And now the research problem is this. So we are interested in estimating the population mean of Y. I mean, we can do more general parameters, but for now, suppose we are interested in estimating the population mean of Y. And then, so theta is in red color because it's unknown. And if pi xi, pi xy is known, then we can easily estimate theta by solving this equation. So here we apply inverse of pi xi as the weight to the equation, to the estimated equation. Unfortunately, in many cases, the PS function pi xi is unknown, and so we cannot apply the estimated equation in one. So many existing approaches use a single model for pi xy, say with the unknown parameter phi, and use the estimated pi hat, which has phi hat in it, and put it in the weight, inverse of it as the weight. So then equation 2 is an equation for estimating theta, but the implicit assumption for using equation 2 is that the PS model is correctly specified. The PS model is correctly specified, and phi hat is consistent. Okay. Now, here's the proposal. The research proposal is this. Instead of employing a single model for pi xy, we consider multiple models, say pi 1 with unknown parameter phi1, pi 2 with unknown parameter phi2, to pi k with unknown parameter phi k. So k can be just some reasonable number like 10, okay? So we consider 10 models and develop a statistical tool for incorporating the multiple PS models. And the claim is this: as long as one of the k candidate models is correctly specified, the resulting estimator is consistent. Okay, so that is good news, right? Because we never really know sure about a single model, but if you can come up with a reasonable 10 models, then the chance of being correct is 10 times high, right? So that is the basic idea, and that is not totally new in some sense, because that has been known to as multiple robust estimation. And Pei-Song Han and Michigan is a pioneer in this direction. And then Sisha Chen and David Hajiza also have papers on these areas. But they all, so the current literature all assume missing and random, okay? And the missing and random assumption of Rubin could be a strong assumption, right? This is not reflecting the reality. The missing and random is popular because it's easy, okay? Because it's easy to solve, not because it reflects the reality. So I'm gonna relax this missing and random assumption here and try to allow for non-missing and random models into the multiple PS models. So that is the basic idea. Okay, so here's the outline of our journey, in our 1 hour journey. So I'm gonna start with the case where pi is known, pi I is known, like survey sampling. And then second scenario is pi is unknown, but the model is known. The model is correct. And third one, which is the most challenging one, is that pi is unknown and we don't know the model either, right? I mean, so that is the final scenario. So so here's the same setup. So we have a pi xi yi from IID. So we observe xi yi only when delta equal to 1, where delta is known to follow a certain model. And here we assume we start with a known propensity score function. So if we know pi xi, so this, if we know pi function, then we can build a likelihood function. So the observed likelihood function is this. So we, for delta equal to 1, we observe, right? We observe everything. So we can write a function. So pi, so pi xi and we have density. And for unknown, so this is the for unknown part, right? 1 minus delta, summation of 1 minus delta I will be capital N minus small n. So that part, we have a missing part. And so we have the information that capital N minus small n of them are missing. So that is the information. And so that is actually has an unknown parameter because, and so that's why I use red color here. So W is the marginal probability of delta equal to 1, which can be written as a integral function of the pi xi, right? So that is basically the expectation of pi xy. So, well, this F is too general, right? And so let's, if we have a density function, parametric model, then we can use this DF as a PDF, right? And so this DF has a integration, the usual parametric integration expectation. So this is very well-known parametric model, observed likelihood function for parametric model. And so and then from here, from this likelihood function, we can take the log to get the log likelihood function, which is basically we have a for observed part we have a log pi plus log f, and then unobserved part we have a log of 1 minus w set. The maximizer of this L OBS is maximum likely estimator. Okay, so that is the starting point. But now we're gonna relax the assumptions one by one. And the first assumption we're gonna relax is the parametric model assumption, right? So rather than assuming a parametric more density assumption, what if we have a assumption zeta is defined through an estimating equation 1. So recall that equation 1, sorry, is, I don't have, I should. So, okay. So suppose I have a, sorry about that. Suppose my model is only this estimating equation generally. Then we have empirical, we may use empirical likelihood. So this is not really new. So this is proposed by Jin Qin and Jun Xiao and Liang, I think. So in CHASA, 2002. So this is the basic, the building block of my proposed method. So the idea is by discretizing F, we can obtain a semi-parametric method called the empirical likelihood method. So pi xi is given, and then the observed likelihood can be written as, so now we have a, here previously we have a zeta, right? And now we have a P. So P is the point mass representing the empirical likelihood. So this is more like a non-parametric likelihood, but we do have a constraint. So this constraint reflects the estimating equation here, right? So this guy is reflected here, and this W theta, W is defined through this expectation, and now this W is defined here, right? Because it's a expectation of pi. So that's why we have additional constraint. In addition to the original normalizing constraint. So constraint 6 is not new. I mean, constraint 6 is just the usual constraint for empirical likelihood, and constraint 7 is used for defining W, and constraint 8 is used for defining theta, and then the 5 is the objective function that actually same form as the parametric one, except that I use the non-parametric likelihood. So that is the well-defined likelihood function, and then we can solve this optimization problem. And now, if you're going to solve this problem, first note that equation 8 does not play any role in determining p hat, because we have a theta. So u and theta has the same dimension. So we have so suppose theta is p dimension, then we have a p additional equation with p unknowns. So it doesn't really add anything new, right? So constraint 8 does not play any role in determining p hat, and so we can just maximize 5 subject to 6 and 7. Okay, so which gives the solution of this form p hat. So we can use the Lagrange multiplier method to solve that, and then lambda hat solves this equation, which basically come from constraint 7. And once we obtain this form, this p hat is a function of W, unknown W, and so we can plug in to the original here, right? We now can write the p hat I W and put it there to obtain the marginal, right? A profile likelihood for W. So we can maximize it with respect to W here only to obtain W hat. And then once we obtain W, so maximize to get W hat, and then this W hat will plug into here, right? And then we can obtain P hat. So that gives the solution. So the final estimator of theta is obtained as the solution to this equation with P hat, and this P hat is a function of W hat. And so the solution is called maximum empirical likelihood estimator. And now turns out that this lambda hat, so if you look at this lambda hat will converge to something, and turns out that this lambda hat converges to this constant capital N divided by small n. And so if some algebra, after some algebra, you end up getting one over, so pi hat is converges to 1 over pi I essentially. So this is actually design weight for Horowitz-Thompson estimation, right? So that's interesting because we end of the day, right? I use this fancy empirical likelihood, but end of the day, I get design weight. So what's going on? Well, so a key technique I employed here is to employ this 7. constraint 7. So that somehow reflects the design and obtain the alternative way of obtaining the design weight. So let's take a careful look at this constraint 7. So we can write it as some orthogonal type constraint. And so constraint 7 is another way of finding the sampling weight for removing the selection bias. And the empirical likelihood method provides an implicit weighting, while the Horowitz-Thompson method provides an explicit weighting, right? So we are not, so we obtain P implicitly. I mean, we obtain the weight implicitly through this optimization problem. So we can call, because this concept is important, we can probably have a name. So I'm going to use the First and Bennett paper. They use a term called internal bias calibration. So I will just use their terminology, IBC condition, because it does the bias calibration, right? But the way they do the bias calibration is kind of internally. So that looks very nice terminology. So and also this is interesting because end of the day W is very close to N divided sampling rate, but actually W hat gives a better estimator. So rather than using this one, we can treat W as unknown and maximize it, we get a better estimator. And also nice thing about empirical likelihood is we can add more constraint if you want. So if you have additional information like this, then we can utilize this information, and so that we probably want to make sure that X satisfies the calibration equation. So we can use that to our optimization problem, and then basically this 12 constraint 12 can be put into the original. So we have 3 constraints, but we can add more, right? So we can put 12 here and solve the same optimization problem, and then we get this solution. So that's no problem. Although if you have too many constraints, then there may be some other issues, but say, so this is, in principle, this is doable. And then let's see what's going on. And then if you use this form, this one, to here, okay, and then asymptotically, we can get this result, equivalence, and the asymptotic equivalence looks familiar, right? And survey sampling, this kind of form looks familiar. That basically is like a regression estimator. But this is a particular regression estimator where the weight has a design-based weight. So this is sometimes called optimal regression estimator, termed by John Rao, Professor John Rao. So that's nice because end of the day, what we used somehow is equivalent to something we know optimal, right? Is known to be optimal. So this is a kind of good news because the regression, I mean the empirical likelihood provides very reasonable estimator that utilize the most of the information in a proper way. Okay, so that is the kind of overview of the empirical likelihood. So there's nothing new here so far. It's just everything is already established. So but we are going to use this analogy to develop our proposed method. Okay. Excuse me. And now we're going to move on to unknown propensity score models. So unknown propensity function. So now the second setup is that we don't know the true model, true propensity score function, but we do have a model. So the assumption is that for some phi, we have equality. So one of the example could be a logistic regression, right? And now to estimate the parameter, we needed some extra information outside the sample. So one common situation is that we have an auxiliary variable observed outside the sample. So for simplicity, we'll assume that X's are observed throughout the finite population. So now the definition of delta is slightly changed because because X's are all observed. So delta refers to the missingness indicator. I mean the response indicator function for the study variable yi. And now we can figure out what is the likelihood function. So we are going to do the same technique. So delta equal to 1, we observe everything. So we can just use that, right? For delta equal to 0, we don't observe y. So we have an integration over y. Because y is not observed, right? But we do observe x. And so the information we have is that for this part, delta equal to 0 is our information. So this is more like I'm not sure whether this is the good notation, right? So this is basically our information, and then after some algebra, we are able to get this from equality. So this equality is interesting because what matters is phi, and and the most of the information is contained in the second term, in the middle, which looks like a likelihood function, right, for the Bernoulli distribution. So essentially, even though delta is pi xi, right? So, even though delta follows the xy is pi xy, but we can take the conditional expectation. So we can take the conditional expectation given x, both sides, right? So that is this way. And then we can treat delta I follows Bernoulli distribution of this distribution still. So that gives justifies this likelihood part. And now question is, how are we gonna compute this one, right? So that is the main problem. That's not easy. I feel that because it involves integration. Is that a question or a noise?
Yeah, so for the audience, could you please mute yourself? There's a lot of noise. Yeah, please.
आप यहीं रुकना, मैं पानी लेके आ रही हूँ, ठीक है?
Okay. So I believe it's noise. So here's a very interesting result established by Danny Pepperman and Mike Shibachkov. So Shibachkov is PhD student of, yeah.
I have one question. Is n very large? Is big N very large?
I'm sorry?
Is big N very large?
Big N?
Yeah, is it very large?
Oh, not necessarily.
Oh, because you assume that the x's are known, are given, right? If
Right.
n is very large, it's impractical to have these x's, right?
So this is just a theory, right? I mean, theory
Okay, I
is
understand.
that,
Yeah, okay. Go on.
so this is the, no matter whether capital N is large or small, the likelihood
right.
itself is correct,
Right, right.
right? So yeah, so we'll worry about all the practical issues later. So this is, valid theory, so we can just use, hopefully we can use it, but whether it's useful or not, that's a different story, right? So okay, so Danny Pepperman and Shibachkov established this result. And why this result is interesting? Because this is difficult to compute. So this is what we are interested in computing. But basically, they provide a formula that bypass this integration by employing a distribution conditional on delta equal to 1, which is relatively easy because we observe x and y for delta equal to 1. So the modeling, right? So here inside this, so the expectation here is with respect to this distribution in the sample. The sample distribution is relatively easy than the population distribution here. So we're gonna use this formula, and actually the formula 15 is not really difficult to show. We can just show it in one page. Basically, if you use this, if you introduce this odd function, so the ratio of the non-response to response probability, and then we can use Bayes formula to obtain the first equality, and this is just the and then we call the first component as O tilde. O tilde is the same odds function using x only, and then now we just take the expectation and conditional expectation, then by definition this is the integration is over this sample distribution. But if you use this equality to here, right, to here, then we have a cancellation, nice cancellation, and so we get this one, and then O tilde x goes outside the integration, and then the integration of density function is 1, so we get this one, which is stable. And then we have a we have a probability, right? So you can see that the 1 cancels, this 1 cancels, and so we get this 15. So I'm going to use this very toy example, the logistic regression model. So remember this logistic regression model, we can write it as a function of odd function. And then the formula, this formula basically implies that we can pi tilde can be just computing the conditional expectation of this odd function conditional on the sample. And then this one is in the logistic regression, this is an exponential function. So if this density is normal, then we can use the property of the MGF, moment generated function, to get a closed form. So we'll go back to this point again. But point is that we can get we can derive, so the result, so this result is not that is useful to computing the marginal probability, I mean conditional probability. so conditional on X. So we can basically obtain the MLE, even non-missing and random, using the marginal, using the conditional, this selection property conditional on X. And so I think we can call it actually marginal because pi xi is good. So pi xi is conditional, right? Conditional. And pi tilde x is, we can call it marginal, because we are integrating out over y. And so we can use this one as if it's a true likelihood function. The tricky problem is whether this has a unique maximum. And so we need some identifiability issue. And we have a very interesting result by Kosuke Morikawa and myself. This is published in Annals of Statistics recently. And so we were able to get some necessary and sufficient condition for the model identification. And basically, as long as this is a one-to-one function of phi, it is identified. We get a unique maximum. So here's an illustration. Suppose this is normal. Then this one is expectation of the OXY phi given x and delta equal to 1. Okay. And now this expectation, and this is an exponential function. So we get a closed form expression. So let's evaluate it. So this is what we are going to evaluate it. Suppose this is normal with the tau x and sigma square. Then the exponential function is just this one using the MGF formula. And look at this. So for example, if phi is a linear function, if phi is linear, then inside the exponential function is a linear function of x. So then it's not really a one-to-one function of phi, because you have a three unknown with two substance statistic, intercept and x. Then it's not really identifiable. So that means you need, so you cannot really use a simple model to get identifiability. So this model should be complex enough to capture the curvature associated with the phi, all the parameters in the outcome, in the response model. So basically, if this is quadratic, so tau x is a quadratic function, then you have a quadratic term here. Then now it is a one-to-one function. So the model is identifiable. So basically, once we are sure that the model is identifiable, then we can estimate the MLE of phi, and then use that to develop the empirical likelihood method. So here's a summary. So using the model, PS model, we can estimate phi by maximizing the L tilde phi using a working model. And then once the phi hat is obtained from step 1, then we plug into here. So this is, remember that this is the IBC condition 7, right? But the only difference is that previously this is known, right? Previously this xi and yi was known, but now we don't know, right? We just have a model, so we need to use this estimator MLE and then plug in and apply to the same empirical likelihood procedure to obtain a theta hat. So that basically solve the problem with unknown phi. Now that's nice, but it relies on strong assumption, right? So the correct PS model itself is a strong assumption. So I'm going to move on to a more challenging setup where unknown, the model is unknown. So in practice, we do not know the true PS model. So we can extend the empirical likelihood method for multiple PS models. So we consider k different PS models and hope that the true model belongs to one of the k candidate models. So this is the basic idea of the multiple robust estimation, which was developed under MAR case only so far. The difficulty of using these multiple models is that we no longer can use the Pepperman-Shevachikov formula 15 because the formula here, the key formula that we used here is valid only when the model is correct. The model for phi xy phi is correct. Is used to establish this equality. If the model is not correct, we don't have this equality. So that means we cannot really use this likelihood function. So we bypass this problem by introducing the outcome model for now. So here's the proposal. So we assume that conditional distribution of y given x is parameterized by this model, conditional model, and then suppose that a consistent estimator of beta hat of beta is available, and we'll discuss how to estimate this. And for each model, so now for each model, we obtain phi hat k by solving the log likelihood function now using the conditional expectation evaluated at this model with at this parameter. So this model is used here in computing the conditional expectation, and beta hat is used here. And once you write it as a function of unknown parameter phi k, then you can basically obtain the MLE for that model. And then we are now going to use similar empirical likelihood technique, but the main difference now is that we have a multiple for all. So for all means that what? All means that we are not going to use the single IBC condition. We have a multiple. So we have a multiple IBC bias calibration constraint. But still, nice thing about empirical likelihood is that constraint we can use multiple constraint. So, but end of the day, we obtain a single set of weight, single weight. So that 21 is interesting. So it is a key constraint. So that constraint is the bias calibration condition for K models. So we can call it as a multiple bias calibration condition. So let's use MBC. So previously it was IBC because we have only one, but now we have a multiple of them. So it makes sense to use MBC. I don't know whether that's a nice name or not. That I don't know, but at least we have a name. So the claim is as long as one of the K different models is correctly specified and beta hat is consistent, then the resulting estimator is consistent. And now here's the big question: how to obtain beta hat? We can think of two approaches. So first approach is a simple but expensive one because we need the additional sample. So So first approach is use a validation sample selected from an independent property sampling. And second option is you don't use the validation sample, but we use a more sophisticated method, which is proposed by Zhao and Xiao. So, so the first approach is, since the first approach is easy, so I'm going to explain it first. So basically, in the first approach, we just use the validation sample to estimate beta hat using the pseudo maximum likelihood estimator, right? So that is this one. So we have an independent validation sample, and we use the weight, so we have no problem in estimating beta hat, computing beta hat. And here's some asymptotic theory. So we have some regular conditions for phi hat estimator should have root 2n consistency. And let's assume that first model pi 1 is correct, and the remaining models is not correct, but should satisfy this constraint. So basically, the model should have the same marginal expectation. And then under these assumptions, we can establish some root 2n consistency. And the influence function here is basically has a zero expectation and finite variance. Okay, so the formula is a little bit ugly, but the bottom line is that we have some root 2n consistency end of the day. So, and the influence function is a zero expectation, because this one is a zero expectation, and this is an influence function for phi hat as zero expectation. So then end of the day we get a zero expectation. So that means the proposed method is unbiased and asymptotically normal if one of the multiple PS models is correctly specified. The asymptotic property of the proposed method estimator holds without requiring knowledge of which model is correct. We don't have to know which model is correct. If we know, then we'll just use that, right? Because we don't know which one, so that's why we're going to use the multiple models. The other working models, PS models, basically serves the another X variable, auxiliary information. And if X's are observed throughout the finite population, we may also include the following constraint to the empirical likelihood optimization. Here's some technical part. So to make sure that we get this nice root 2n consistency, we need this 24. So 24 means looks easy, right? I mean, this marginal, the marginal probability of the working model should have the same marginal probability, which is reasonable assumption, but whether this is also how to check this assumption is difficult. Because so why this is difficult? Because let's take a look at 24 more carefully. So 24 is equivalently expressed as this condition. So basically, some of the population, some of the pi k's in the population level should add up to the same marginal. So if you take the divide both sides by capital N, this is just the sampling rate, right? So this is 27. Satisfying 27 is important. The problem is that we don't observe yi outside the sample. So we don't know. We cannot really check whether 27 is correct or not. So that's why we use this 28. So, so 27 is a supposed condition for 24, which is the condition for the root inconsistency. But 27 is difficult to achieve. So that's why we use 28 to bypass imposing 27. Okay. If the PS model is missing a random, then we observe xi throughout the finite population. So we can actually satisfy this condition automatically. So MAR, no problem. But non-MAR case, we don't know. We cannot really be sure about 24. So that's why we use this one to impose to get this condition. So 28 is used to get key condition 24, and that 28 is satisfied if we use the maximum likely estimation. So now we're gonna move on to how to estimate beta hat, and probably I don't have much time. Well, how much time do you want to give me, Changbao?
You can have at least 10 minutes.
10 minutes, okay.
Yeah,
Thank
no
you.
more than 15, please.
Okay, thank you. So I may a little bit speed up. So pseudo likelihood approach is proposed by Jun Xiao, and Jiwei Zhao is the former PhD student of Jun Xiao. He's now back to Wisconsin. So to apply the proposed method, we need a constant estimator of beta in this outcome model. So basically, we are interested in estimating beta without really specifying a model for the response mechanism. So Jun Xiao and Zhao developed a method, and they build on this method based on the assumption that often used in missing data. So non-response instrumental variable assumption means that some of the x variable, so x1 is important in predicting delta, but x2, so x2 is not really used. So here x2 is a free of x2, right? But this x2 is still helpful in determining y. So that is the key assumption. So here's another. So instrumental variable assumption is this one. So you can see that x2 still important in predicting y, but the connection, so there's no direct connection to delta. Okay, so x2 is a little bit irrelevant to delta as long as y is included in the model. So that is the key assumption, and that instrumental variable assumption, and how to find a delta. So x2 instrument variable has been explored in by these co-authors. So now under this instrumental variable assumption, basically the key idea is x2 y x1 is p x2 given y x1 delta equal to 1 under by 29. So 29 implies this. And because of that, because of the conditional independence, we get this equality. Because of that, we can just only use the observed case only to obtain this, to use this for likelihood, construct the likelihood function. And this one turns out to be written as this way. And so we have a parameter here of interest here, and then this is the kind of nuisance model. And then we can, as long as you have a constant estimator for this conditional model, then you can construct a conditional likelihood. And remember that X's are all observed, right? X's are all observed throughout the population. So it's not really difficult to obtain a constant model. So here's a simulation study. We have a finite population of this size, and we generate X1, X2, X3 here. And Y is a linear function of the X1 linear model. We generate delta from Bernoulli distribution with the probability X1, X2, Y under the different scenario. So X3 is intentionally skipped here, right? So X3 is not here because we want to satisfy the instrument variable assumption. So X3 is used in constructing Y, but not used in constructing delta. And we observe Yi only when delta equal to 1. We observe Xi throughout the finite population. So we considered 4 different scenarios for the selection: missing and random, not missing and random, not missing and random, another random. So missing and random, we use X1 and X2. Not missing and random, we use X1Y, X2Y, X1, X2Y, very weird Y. Okay. So basically, this is the kind of very weird non-missing and random, and see whether it works well or not. And notice that X3 is the instrumental variable. And so we need to fill the model to obtain. So we use the normal linear regression and to construct the nuisance model. And then we construct the conditional likelihood and apply the Zhao and Xiao method. And PS model, we consider following 3 models. So RM1, RM2, RM3. So, sorry, I'm really sorry. This is Y. Yeah, I sorry about that. So, yeah. So basically, I used, so because we generated this RM1, RM2, RM3, RM4. So we use this one as a true model. We use this one as the true model. We use this one as a true model, respectively. Okay. So that is this model, RM1 and RM2, RM3. And then from each model, we apply the proposed method. We can obtain for each model, we can just use because we know beta hat, right? We can compute the marginal probability, marginal PS probability, and then obtain the likelihood and maximize it. And to get phi hat. And so EL1 and EL2 and EL3, just to use a single model. For each PS model with estimate parameter phi hat k, we apply the EL method as follows. So we maximize this one subject to this constraint and this constraint as a constraint for the EL optimization. And then EL estimator is obtained by the solution to this equation. MEL, this is our proposed method. We now use three models all together into the constraint and obtain the MEL. Here's a simulation result. RM1, remember that RM1 is the MAR model. So so EL1 works very well, but EL2 and EL3 fails. And MEL is okay, but has a larger variance. RM2, so EL2 uses the model for RM2, right? So EL2 works very well, but EL1 fails now because it uses the wrong model. EL3 fails, but MEL still is okay, even though we have a slightly higher variance. RM3, now EL3 is okay because EL3 used the RM3 as the true model, but MEL fails. RM4, we don't have the true model, right? RM4 is very weird model. So they fails, of course. Our method also fails slightly, but not that bad, right? I mean, so that we are not 100% corrected, but maybe 90%. So that seems to be much better, at least, than a single method. So the EL-based method based on a single PS model is unbiased and efficient under the correct model setup, but it is severely biased when the PS model is not correctly specified. Not surprising. The proposed EL method incorporates the multiple PS models through MBC condition shows good performance for all scenarios considered as the multiple candidate models contains the true model. Even when the multiple PS model do not cover the true PS model, as in RM4, the proposed method shows the smaller biases than the other PS estimators based on the single PS model. So our method is biased, but still much better than the other competitors, right? And under the correct model, the EL method using a single PS model is more efficient than the multiple PS models using multiple PS model. It is because the MBC condition sacrifices the efficiency to obtain multiple robustness. Okay. The problem can be extended to data integration problem. So in the proposed method is developed on the setup of balanced sample where X's are all available throughout the finite population. We wish to apply the proposed method under the data integration setup where there are two independent samples with the same measurement. One is probability sampling and the other is non-probability sampling. So data A is a probability and data is non-probability. So sample B is representative is no, but the cost is low. So maybe that's popular, right? I mean, it's attractive in terms of the cost, but scientifically it's not really useful. But because we have a probability sample, now the question is there any way we can, utilize and combine them together and get some multiply robust. So basically we wish to consider multiple PS models and develop the multiple robust estimation method. And we do not need to specify the outcome model. So basically idea is that for each model, we have a way to estimate the phi. And the basic idea is that if you carefully look at the log likelihood function, we get this one. And then this is basically the another expression. And this one, the first term is the quantity in the current non-probability sample. So we can observe everything here already. The second term is the finite population quantity, and it can be estimated from the independent probability sample. So this is the proposal. So basically, we can just use the Horowitt-Thompson estimator for the second term here. And Ti is the sampling weight for sample A. So we have a sample B here, first term, sample A in the second term, and design weight here. And this idea is not really new, because Chang Bao and his student Yilin Chen developed this method published in JASA under the MAR setup, and they have developed a very nice data integration method. So this is kind of a extension of their method to non-missing and random and multiple models. So basically, once we can obtain this one for each model, then we can apply the same MBC empirical likelihood method like this. So basically, we obtain phi hat k and then put the constraint here multiply, and then after that we solve it. So constraint 39 is another MBC condition, and claim is that as long as one of the k models is correct, the resulting MLE is consistent. And unlike the existing multiply robust method, our method can include both MAR and non-MAR models. So summary, we have developed a unified framework for handling selection bias with a known PS function or with unknown but multiple PS models. By making the overall PS estimation less dependent on the PS model assumptions, we can analyze the voluntary samples safely if one of the two conditions holds. The first condition is, suppose you have a voluntary sample, calibration sample, then with the same measurement, then no problem. Or if you have an instrumental variable, then we can apply the Zhao method and obtain a constant estimate of beta hat, and then we can apply the MBC method. If the cost for collecting the voluntary sample is much lower than the cost for collecting a probability sample, the proposed method can be a cost-effective statistical tool for obtaining survey data, removing the selection bias. That is, we can develop a cost-effective survey design with two modes of sampling. Okay. So we have several future research topics. One is the semi-parametric efficient estimation of beta for utilizing the ML method, optimal sampling design for data integration, and we also need to do real data application. So this is all. Thank you very much for your attention.
Thank you very much, Jae, for a very nice presentation on this very important topic. Before I open the floor for questions, can I ask you a few minor things for clarifications? Yeah, sure. Okay. Can you go back to your slides, page 4?
Yeah.
At the beginning of your talk.
Right. 4, yes.
Okay, good. So one of the ideas used in this presentation is multiple models. Okay, multiple models on propensity scores. Can you just give the audience a simple example where you could have 2 or 3 different models for the propensity score in practice?
Ah, I see. Well, so, okay. Here's probably one example. So you could use MAR, right? I mean, so suppose you have you don't know whether MAR is true or not. Then one simple way is maybe consider both 2 models, right? One model using MAR and maybe the other model using non-MAR. Like
right,
what I did
yeah.
in my
so
simulation.
when you say the model based on MAR basically involve X only, right?
Right, yes.
And then is that the case if I have a model involve both X and Y? So this is more like a 4 model.
I see.
the model involve X only is more like a submodel. Is that true or no?
That's right. Actually, that's a very important point. So you might wonder, why don't I just use full model, right? And I mean, very flexible propensity score model, and then can just so you have all the interaction term and X and Y and all the interaction term of X and Y to get a full model, full PS model, and then use it as a single model. Where the problem with this full model approach is that you have an identifiability problem. Remember that when non-missing and random, right? You don't have enough information to estimate all the parameters. So you need some sort of the identifiability issue. I mean, you need some sort of the reduced model to avoid the non-identifiability issue. So that's why you may need to consider several different simple models, reduced models, and that's why you may end up getting multiple models.
Yeah, so clearly there are issues of do you want to include interactions terms in it? The other things with the propensity score models, because it's a model based on the binary response delta. So I would imagine people would wondering what kind of link do I use, right? Do I use a logistic model? Do I use a probit model? Do I use a complementary log? So this probably is the things you can think about when you actually have multiple choices in terms of a working model. Okay, so that's the first thing. Can you scroll down to page 11, please?
Sure. Okay.
Okay, yeah. So the W is the marginal probability of delta I equals 1.
Right.
So intuitively, the W is supposed to be the sampling fraction, little n over capital N.
Right.
And then you have the statements here. If you put W as an unknown parameter in that estimation process, it's more efficient than by actually putting this sampling fraction in.
Right.
Are they asymptotically equivalent or they are very different?
So basically, this so if you so actually this W hat will converge to this one, but finite not well. I don't remember exactly, but some so I'd say this will converge to W star, which is very close to n over n, but not exactly the same, and that's why we get efficiency gain. So conceptually, right, we search over all W, and this W hat. So the solution to this is not necessarily equal to. So the solution W hat is not necessarily equal to n divided by n, capital N, and so the conceptually this maximizing this one should give the better result, and actually it does, and we did have some simulation and theoretical result to get this result, but because if you think about this design optimal estimator, right, and even if you don't have the X information, you still utilize better estimator because you get intercept and you use intercept information to get design optimal regression estimator.
Right. Yeah. So the efficiency you see is actually from simulation studies. It's not really something you can show in theory. Say the asymptotic variance is smaller.
Yeah. We have a theory.
Okay. Okay. Good. So if you do have a theory, and that would be something very interesting to see. And I can imagine in simulation studies you do have such observations. Can you move to page 27, please.
Yeah. By the way, let me just so this is not really new. I mean, Liu and Fan, I think they actually proved theoretically that this W hat using this empirical likelihood. So the claim here can be credited to Liu. I think they are Fan.
Yeah, is that the recent archive paper?
I think, yeah, that's a recent archive paper, right? Yes.
Okay, good. Yeah. Can I see your slides on 27, please? Page 27.
Sure. Okay, here.
Okay, so when you say the proposed method is unbiased, do you mean your estimator is consistent? Not
right.
estimator is not exact unbiased, right?
Right, asymptotically, sorry, yeah.
Yeah, okay. That's what I'm imagining, because usually you don't get exact unbiasedness. Maybe I'll just finish by one more comment on your page 43, then I will leave the door open for other people to comment.
Okay.
Yeah, yes, yeah. I think this extension is important because these days non-probability samples is a big topic. There's a lot of research things going on. The extension you just described here has no issues. Okay, so everything is fine. I just want to make a comment here about the setting. So when you have a probability sample A and a non-probability sample B, and the setting here you use is you observe XY in both samples.
Right.
And in reality, that's a very restrictive setting, because oftentimes what people usually have is you have a lot of variables observed in the non-probability sample. And then for the probability sample, it's not really something you conducted. So the probability sample is typically a large survey is already sitting there. Okay, it's an existing survey.
Right.
And they only have some of the variables you may have an interest, such as some of the demographic variables. And in particular, some of the specific study variables, Y in a non-probability sample, they are often not available in the probability sample. So I would imagine that would be a potential research topic here. So what happens if Y is not available in the probability sample? And then how do you implement the strategies you described here? So that's just my comment. So now the floor is open. Anybody, if you wanna ask a question, just unmute yourself, please.
Hi, Jay. This is Yumo.
Yeah. Hey.
Yeah, Jay. Thank you for your talk. I'm sorry that my camera does not work properly. So, yeah. So let me just directly ask you a question about your equation 28.
28. Okay. Yeah. Okay.
So here you said equation 28 can be automatically satisfied by the property of maximum likelihood estimation, right?
Right. Yes.
What I'm thinking is that this property require logistic regression model.
Ah, that's very good point. Right. I think not right. So this is, yeah, I agree. So this is, it's not true for all models, but true only for certain models.
Yeah, and I also have a question. Even if we have a logistic regression model,
okay.
For example, if we have a logistic regression model for delta given X and Y, but after you integrate out Y, do we still have a logistic regression model?
No, well, not necessarily, right. That's a good point. So 28 implies 24, but whether 28 is really holds, whether 28 holds really, can be a question. That's right. So we need to think about, make sure how exactly under what condition we can satisfy 28.
Yes. Okay.
Yeah.
Thanks, Jay. So probably
Thank
I
you.
can talk with you later more.
Yeah,
about
yeah,
that.
very
So,
sharp question. Thank you. Thank you. Yeah. Right.
So Jay, actually, that's one of the questions on my long list. I think for the equation in the middle to hold, not only you need the pi x has a logistic form, you also need that logistic regression model has the intercept. Otherwise, it doesn't work.
Yeah, yeah, right, sure. Yeah, right. Yeah, that's right.
Okay, good. Other questions, please.
So can I ask another question? Sorry.
Yeah.
So Jay, I noticed that you use like a instrument variable approach to estimate the beta,
Right. Right.
So can we prove like efficiency by doing MBC? Because if you do have an instrument variable, right, so you can just go ahead to estimate beta, and through beta you can estimate
We didn't hear you well. We didn't hear you.
Sorry.
For all the things. You may want to just repeat what you just said.
Can you hear me now?
Yeah.
Yes.
Okay. Yeah. My question is, by doing MBC, can we achieve more efficiency than doing the instrument variable approach?
Well, actually, MBC is a tool for bias correction. Actually, if we notice that if you add more models, we sacrifice efficiency. So it could be a really interesting problem how we balance the bias and variance trade-off, because seems to be that the number of models actually has a, so if you increase the number of models, then we have a protection. We can achieve the bias calibration, but we sacrifice the variance. So we sacrifice the efficiency. So my short answer is that the current methodology didn't really care about the efficiency problem. We mainly focus on bias issue, but that could be an important future research.
Yeah, thank you very much, Jay.
Yeah,
thank you.
Thanks. Yeah, very good question. Thank you.
I will give you one more chance if anybody want to ask a question, because we're getting close to that 1.5 hour mark.
Hey, Jay,
Yeah.
in the MBC method, you're assuming that at least one of the models is correct. Are you doing
Right.
that?
Yeah,
Suppose
yes.
they're all wrong. Suppose they're all wrong. How would you know that?
Well, so theory, I mean, to develop the theory, right? I mean, that is really a reasonable question and practically important. But if you want to develop a theory to show consistency, what would be the minimum, the weakest possible assumption, right? If you think about that, how can we avoid assuming that at least one model is correct? Impossible.
Possible, huh? So we don't know whether the model is correct, just like if we know, just like if we have one model only. We don't know if that's correct either.
Exactly, right.
You're
right.
saying because we have more models, we have a higher chance of one of them to be correct.
That is the kind of common sense, right? I mean,
yeah.
You can actually put a probability statement very easily. For example, if you have 3 models, each model has a 50% chance to be correct. Then the probability of at least one of the 3 is correct is actually 7 out of 8. So you do have a larger probability. All right, I think we are at this 1.5 hour mark. I want to thank Jay. You have another question here?
Yes, sir. Yeah, good evening, sir. I am Lakshmikant Dwivedi from IIPS Mumbai. Yeah, just you
Please
are.
go ahead.
Yes, sir. Thank you, sir. Just we are working in the applied science in the demography. You are doing the application of propensity score matching, and sometime once we are sending the paper, generally you receive the comments that how do you best apply the sampling weight, and to what extent your result will get changed after application of the sampling weight. Another important one is that if there is a unobserved factors are playing a key role in the matching of those who are receiving the treatment and not receiving the treatment, then what would be happen? I mean to say, if there is a reverse causation is there, sometime why is your dependent variables affecting the independent variables? In that case, how this model will work? So we are actually generally we are not able to, if there are so many unobserved factors are there, then our results are generally unreliable. So I don't know how to handle that one, sir. Maybe.
So I'm not sure whether I understand correctly, but if I understand correctly, your question is, suppose there's a unobserved variable that really affect the response mechanism. And then,
yes.
Right? Then how, well, actually, that's a good question. Actually, I thought about that before. And my answer is that you don't have to. So let me share a screen and write down my answer. So my point, so I do have an answer. So basically your delta is a function of some function of z. And z is never observed. And now the question is, how should we do that, right? And so my answer is that you don't have to worry about that. All you have to worry about is you need a model. As long as you have a model for this, so that is pi x and y. Okay, so this one matters. So you don't have to know, no problem, because we observe this, right? Observe at least at delta equal to 1, we observe this. That matters, and actually that is the basic idea of weight smoothing. You even if you have a, Professor Rao say this, or I mean, find out already long time ago, if you have a totally irrelevant design variable, should we consider that into your estimation? Well, if that's totally irrelevant, then you don't have to. I mean, that is the basic idea of the weight smoothing. So my point is that what really matters is should be relevant to our analysis. So because our analysis is of about relevant to x and y, right? Theta is relevant to x and y, and so we do need to conditional on x and y. That actually gives a better estimation. Even if you know this, so another way saying is, even if you know this, it's better to consider this one. That's better, gives a better estimation. Is that answers your question?
Okay, sir. Okay, sir. Thank you, sir.
Yeah, no problem.
Okay, I think it's time to wrap up this talk. So first, I want to thank Jae for the excellent and stimulating talk. And apparently, it generated a lot of questions and further thinking. So I'm just finished with a very few additional words here. I thank our colleagues and friends from SSCA organizing this webinar series, and I'm honored to be part of it. I think the field of survey sampling is relatively young. We all know the foundation of design-based inference started from the 1934 paper by Neyman, and a lot of development started in the 1940s and 1950s. And of course, most of this activity is in the US, but it's also elsewhere, including India. So I would say India is the land that produced so many world-class statisticians, including the field of survey sampling. So I want to mention two names here because I have to. One is Professor V.P. Gadambi. Professor Gadambi is on the faculty here at Waterloo for many, many years. And he passed away in 2016 at the age of 90. And his most famous paper is probably the 1955 JRSSB paper on the non-existence of the best linear unbiased estimator, which generate a number of research directions in the years to come. And the other name I have to mention is Professor John Rowe, known in the academic world as J.K. Rowe, and who is actually, I believe, is the inaugural speaker of this webinar series. And John is the living legend in survey sampling. Before I connect some of the dots, I want to mention another name, that is Wayne Fuller. Okay, so Wayne is well known for his work in measurement errors, time series, and of course, in survey sampling. So when Jay finished his PhD with Wayne Fuller, as you can imagine, it is very natural for Jay to be connected with John Rowe. And I think that's a good thing for our field, because together they produced many excellent research papers and moved the field forward in a number of different ways. So I myself had the privilege to work with both John and Jay and on several research projects. And indeed, Jay and I recently, we had a joint paper with our students published by JRSSA on dealing with non-probability samples using mass imputation. So which is also related to the topics Jay presented today. So I hope the talk given by Jay today will stimulate some interest among our audience, especially some of the young researchers. And there will be further development, further research done on this very general topic of data integration, which becomes very, very active these days on combining data from different sources. So once again, I want to thank SSCA for organizing this event and thank Jay for the excellent talk. And here you go, Dr. Dandapani, is back to you.
Thank you. Before I propose a formal vote of thanks, I would like to read the message from Professor Gupta. In fact, he's very sad that he missed it. So I'm just reading his message. He messaged me. Dear Jae-kwang, Professor Rao, all distinguished participants of this prestigious seminar, my unconditional apologies to all of you for not being able to join you. This was one event I was looking forward to with great enthusiasm, but the technology came in my way. I wish I were smarter to handle technological glitches, but at my age, we fear these technologies. I missed a grand talk. I missed the opportunity to meet all of you. It has been my loss. My apologies again, and I seek your pardon. maybe some other time I will get an opportunity to meet you all. Till then, stay safe. So it seems he was trying to connect from multiple devices, but he could not succeed, and that's what he was messaging me. I asked him to join through mobile also, but somehow he could not join. So sorry from his side. And so let me just briefly propose a vote of thanks at the outset on behalf of the Society of Statistics, Computer and Applications, and on my on behalf of all the participants of this workshop. I take this opportunity to place our thanks and appreciation to Professor Jae Kim for delivering a wonderful talk. Professor Kim, you have touched the many important statistical issues in propensity matching models, which is fastly emerging as a basic a tool in applied areas, particularly by social scientists. So it has also provided young researchers to update their knowledge on these issues. In fact, this is the second topic on combining information from multiple sources. The first one was by Professor Rao himself. He is also there. He has also joined, but I think he is not switched on his video. But I thank Professor Wu for conducting this session wonderfully, and also, I mean, initiating a stimulated discussion on various issues. And I also thank all the participants and all the, I mean, we have about 40 or 45 people who joined at one point of time. So we take this opportunity to thank each one of you for supporting this activity of SSCA. And in fact, we will be having the third event on this series on 2nd of September on linear algebra. The speakers are Professor Simo Punatin and Professor Bikas Sinha and 2-3 more. That will be on 2nd September, Friday. It is almost at the same time, 6:30 p.m. in India time, the same time as we started today. So thank you one and all, and have a safe day, and have a good day ahead. Thank you one and all. Thank you.
Thank you so much.
Thank you.
Bye.
Bye.
Bye, Kang-bao.
Bye-bye.
Bye. So I'm ending the meeting for all.
Yeah.